Hello everybody. Well, welcome back to the Gregorius Maths video. Yes, so today we're going to be talking about the second isomorphism theorem because, well, we've already talked about the first isomorphism theorem, and we've already talked about the third isomorphism theorem, so it's only right that we complete the set, sort of, we go for the second isomorphism theorem. And yeah, today we're going to be looking at it from the viewpoint of lattices and lattice theory, just to give you a little maybe a different perspective on what's going on here. So what's the theorem? What's the statement? What's the theorem that I'm actually talking about? The theorem is that if you have a group G and you have a subgroup H of G and a normal subgroup N of G, then we have an isomorphism between the sets Hn mod n and H mod H intersect n, where this Hn is just the product of groups, i.e. just the set of all elements, the subgroup of all elements of the form Hn, which is allowed to be a subgroup because n is normal. Okay, so how on earth are we going to bring, well, okay, before I start talking about how we're going to bring lattices into the question, I should probably say what a lattice is first, or what I mean by a lattice in today's video. So a lattice is a partially ordered set, L, and what do we have? Well, it also comes equipped with the following two operations, if you like. So we have, given a two-element subset of the lattice, we have a least upper bound, and that is called the join, A join B. And we also have a greatest lower bound, and that is A meet B. So we call the least upper bound A join B, and we call the greatest lower bound A meet B. Okay, and we could also define a lattice in terms of these operations as an algebraic structure and then use these operations in order to obtain a partial ordering. So it can go either way, but in general we have a partial ordering and we have these two operations as well. So, okay, again, how does this relate to what we're talking about today? Well, here's a little sort of a hint that maybe we can talk about groups here, is that if you're given a group G, then the set of all subgroups of G, along with set inclusion, gives you a lattice. And, well, the natural questions to ask are, what are the join and the meet? Well, the join, or no, the meet is easier. So A meet B is just equal to, well, sort of the least, as the greatest lower bound of this set would be A intersect B. Okay. And, well, what's the least upper bound? Well, we probably would like to take A union B, but that is definitely not necessarily a subgroup of G. So instead, we have to take the subgroup which is generated by A union B. And, well, when A or B are normal, this can also be just thought of as the product, the group product AB. Okay, now, so here's the meet and here's the join. And we see that since n is normal, really this second isomorphism theorem is telling us something about the meet and the join in this lattice of subgroups of G. So how can we make this precise? How can we, make this precise? And, well, before we proceed, a really important property of subgroups here is if you have ABC, where A is a subset of C, and they're all subgroups of G, we have what's called the modularity condition, or the modular property for groups. And that is that as sets, because we're just working with subgroups here, as sets, the set given by AB intersect C is equal to A and then times or product with B intersect C. This is known as the modularity condition, when A is a subset of C. Okay, I just wanted to get that out of the way. Okay, now, how are we going to relate this back precisely to the second isomorphism theorem? So, okay, you can say something vague like the second isomorphism theorem is a statement about the join and the meet in the lattice of subgroups of G. But we can say more. So let's take a closer look at what's really happening here. So we're going to start by considering the following two intervals. So we're going to consider the interval between H intersect N and H. And we're going to consider the interval given by between N and the product Hn, like so. Okay, and firstly, what are these intervals? These intervals are, well, this one here is the set of all subgroups L where H intersect N is a subset of L, but L is a subset of H. So, you know, natural definition. And here is the set of all subgroups such that N is a subset of it, but it itself is a subset of Hn. Okay, so this is sort of what you would expect the definition to be. And I claim that there's a lattice isomorphism between these two intervals, where a lattice isomorphism is just like a bijection that preserves the join and the meet type of thing, you know, what you would expect again. Why can I claim this? Well, I claim this because I say, okay, I'm just going to construct the maps explicitly. So I'm going to construct the map from here to here, phi, let's call it, so that phi of L is equal to, well, if we're taking in an element of this interval and we want to get an element of this interval, a very natural one to choose would just be L, the product Ln, which you can pretty clearly see lands within this interval somewhere. And what else do we have? Well, we need an inverse to this map. And, well, notice that I'm taking phi of L to be L join N, like so, because notice that N is normal, so the product is just the join. So you might think, okay, well, why don't we just define the inverse to be K meet, and then we took the join of N, so why don't we just do the meet of H now? So I claim that these two are inverses, and I'm going to show one direction and then the other direction you can, you know, do for yourself if you're really interested. So if we just do phi of psi of L, or psi of K, I guess I should be consistent, is, well, this is phi of, and again, notice that K intersect H will land within here, right? Notice that, because K is somewhere between N and Hn. So K intersect H will be somewhere between H intersect N and, well, Hn intersect H will just be H, so it'll be somewhere in between again. That's probably should have pointed that out, but whatever. Okay, so we get the composition phi psi of K is phi of K intersect H, which is equal to K intersect H times L, sorry, not times L, times N. And N is a normal subgroup here, so we can just swap the order, if you like. And essentially we can get it precise. Okay, intersection is commutative, and N is a normal subgroup, so we can bring N to the front here. So we have no issues bringing it exactly into this form. So I can tell you that this is equal to K intersect Hn. And this is equal to, well, Hn, by definition, K is somewhere in between N and Hn. So more specifically, K is a subset of Hn, and so K intersect Hn will just be K, like so. And so, okay, we get inverses on that side. And again, you could show that psi of phi of L similarly is just L. And so they are inverses. And you can check that they preserve meets and joins or whatever, but they do. So we've constructed this isomorphism here. And well, now something a bit more precise is happening because, well, is it just a coincidence here that these two subgroups are precisely these ones here, and these two subgroups are precisely these ones here? Like, is that a coincidence? I don't think so. So let's crack on and get to the bottom of proceedings here. Let's see what's happening, you know what I mean? So, okay, well, apologies. Anyway, let's move on. Okay, here's where the connection really comes into play. This interval here, I claim, this interval between h and h intersect n is isomorphic to the lattice of subgroups of h mod h intersect n, like this. Sorry, I just wrote these the wrong way around, but pretend I solved them. I'll just like that. Now, why is this? Well, we can construct a very natural map. So if we take some subset L, we'll just map it to L mod h intersect n, and this clearly gives us a bijection because every subgroup of h mod h intersect n will be of this form, so you could just map it straight back to L. So you pretty easily get a isomorphism here. And by exactly the same reasoning, we have that the interval between n and hn is isomorphic to the subgroup of the lattice of subgroups of hn mod n. And so since these intervals are isomorphic, you get that the lattice of subgroups of h mod h intersect n is isomorphic to the lattice of subgroups of hn mod n, like so. And here you might think, oh, and then we can conclude that the second isomorphism theorem is true and we're done. This is not quite true, since it's not in general true that if the lattice of subgroups of two groups are isomorphic as lattices, then the actual groups themselves are isomorphic. So we need to do a little bit of work. So let's think about what the isomorphism between these two lattices is. And again, it pops out quite naturally. So we take some subgroup which looks like L mod h intersects n, and we just send that to Ln mod n, like this. Okay, good. Why is this good? Well, this can be seen. What you have to notice now is this map here is induced by the map from h mod h intersect n into hn mod n, which sends some coset h intersect n to hn, like this. So this isomorphism of subgroups is induced by this map, where by induced I mean you take this map and you use it to define a map from the subgroup lattices, where some subgroup L gets mapped to the image under this map. So if we call this map P, gets mapped to P of L, like this. And if you look at what happens to L, well, P of L would be the set of all. You take a subgroup like this, it looks like this, and you send it to the set of all Ln, where L is in L, which is precisely this subgroup here. And so what I'm saying is that this isomorphism, this lattice isomorphism, if you notice that it's induced by this map, then the isomorphism between these two groups, which is given by the group isomorphism, which we want from the second isomorphism theorem, pops out quite naturally. That's what I'm trying to say. And you can check this as an isomorphism if you like. But yeah, so, okay, what am I saying? I'm saying that this, okay, let me try to wrap this video up in a satisfactory way. The second isomorphism theorem, you can think of it as a statement about the joins and the meets within the lattice of subgroups of G, and you can think about it as popping out naturally from this lattice isomorphism of the subgroup of the subgroup lattices, basically. So it pops out quite nicely. And yeah, I don't know. I hope that somewhat makes sense. I don't know if I explained that the best, but I hope that this gives you a slightly different perspective on the second isomorphism theorem, and that you enjoyed. And yeah, I'll see you maybe tomorrow at some point soon. Yeah, I'll see you then. Ta.